So the objective of this video is to provide a broad overview or a working definition of what it means to be an engineer and what the field of study of engineering is. And if you reflect back on the learning outcomes of our course, you realize immediately that really this lecture is kind of a summary of what the entire course is about. So really by setting a working definition, we're going to be able to iteratively improve upon our understanding of the meaning of these words throughout the remainder of the course, which ironically is really one of the characteristics of the engineering process, specifically engineering design, through iterative improvement. So if I had to have you take away one thing from this lecture about what the definition of an engineer is, and what I mean there is kind of from a vocational perspective, along with what engineering is from a field of study point of view, I would want you to understand that amongst all the stakeholders that matter, so the engineers themselves or the people that hire engineers and so on, the definitions of those two terms vary substantially. There is no right answer. It's not a deterministic law that you can memorize and everyone in the population that matters, their opinion agrees. So really what you're looking for is a general framework that's consistent with the way that we understand vocational terminology along with fields of studies across the entire disciplines. And I'm going to kind of speak in that ambiguous language and we'll try to build up from there. So when I think about what makes the vocation of someone, the job that they actually do, what I think about is what tools do they have at their disposal and what kind of problems do they work on. So if you look at that initial bullet point in the upper right corner, you will see that that kind of reflects that sort of framework of definition that I just set. And when I think about engineers as a vocation, I think about them, and most people would agree, as people that have a toolbox available to them of science and mathematics. And maybe you could expand upon that and say science, mathematics, and technology or computing or so on. But since all of those can kind of be viewed as subsets or realizations of science and math, I'll keep it general and I'll just say our toolbox is science and mathematics. So that's what we were able to use to solve problems. But moreover, maybe the more differentiating thing about what makes an engineer versus someone that's working in the pure sciences like chemistry or physics or so on is our sole objective is applying those tools in our toolbox in order to solve problems that impact people or improve quality of life. And I think when you think about the compensation aspects of engineering that we'll talk about a little bit later, it reflects the fact that we're working on problems that matter. So we have several engineering processes within our domain that we'll look at a little bit later in the course. We have the capability to do optimization and design. We have the capability to do maintenance of existing solutions that engineers before us have developed. And it's important to realize that when you think about the tools that we're either designing or maintaining, they're not necessarily physical things. They're not necessarily hardware. They could be software, and they could just be processes. I believe that oftentimes when individuals take this course, some of you are interested in operations research or supply chain management. That certainly would be hard to classify uniquely as either hardware or software. It's more of process engineering. So anytime that you're applying the principles of science and mathematics, you're solving problems that impact human well-being, and you're doing those various engineering functions of product design or maintenance, probably most would agree that you're doing engineering type work. So we all know that there are various sub-disciplines within engineering: mechanical engineering, electrical engineering, chemical engineering, and so on. And when you think about what distinguishes them from one another, kind of building upon the definition that we have above, one could naturally argue that not only do the application domains differ, meaning what type of, when we're working on those problems that impact people, what kind of problems are we working on? Are we working on the design of new propulsion systems or new energy systems? Are we working on new computing systems and so on? So clearly that's one of the ways that the subdisciplines of engineering are distinguished. But another thing that I would argue, and I think it's reflected in the programs or fields of studies for the various subdisciplines of engineering, is that the tools that are available at our disposal, I shouldn't say the tools available at our disposal, but the ones that we really focus upon are, particularly within science, are distinguished across the engineering disciplines. Well, what do I mean by that? Well, all of you, to get an engineering degree, will likely have to take a second university physics course, which focuses on the domain of electrodynamics, and you'll be introduced briefly to the idea of Maxwell's equations. But if you're working in civil engineering, the odds that you will crack those out of your toolbox and use them again are pretty low probability. Versus someone that's working in antenna design for maybe 5G systems, they're going to be using those principles on a daily basis. So another thing that differentiates the subdisciplines of engineering is what subsets of sciences, and you could even argue subsets of mathematics, that we're focused on. So what kind of defines engineers from a compensation and vocational point of view? Well, most people agree that engineers are well compensated, and that is certainly true. And most indicators of the employment prospects of engineering are stable or growing, depending upon what particular subdiscipline that you're working in. However, one of the things you want to be aware of, if you follow that link to the Bureau of Labor and Statistics, is there is considerable variability in compensation and general employment opportunity across the various engineering subdisciplines. And a lot of that is actually driven by geographic factors. And why do I bring that up? Well, oftentimes people will send me an email or they'll come to my office and they'll say, I really don't know what subdiscipline of engineering I want to pursue. And one of the weirdest things that I'll ask them, they always are a bit set back about this, is, well, where do you want to live in the country? Because one of the things that you will find if you dig into the data is some subdisciplines of engineering are the employment opportunities are more clustered by the associated application domains or industries within the country. So hard to argue, even with the shift of manufacturing out of the Rust Belt over the last few decades, that one wouldn't have more employment opportunities available to them in mechanical engineering, particularly designed for automotive or cars in the Midwest, than they would, I don't know, maybe in South Dakota or New Mexico. So when you think more in more detail about the engineering subdisciplines and the way that they often come about, usually what happens is there's some specific industry demand that follows the creation of whatever supporting scientific principle was invented a priori, and then that will cause academic institutions to create relevant academic programming or degrees in those subdisciplines. So the workflow is you have some type of scientific advancement that spurns some type of industrial advancement and job opportunities. And the employers in those new industries need dedicated employees with particular skill sets. And they go to higher education and they say, hey, your current degree plans, you can't train anyone with the specific skill set that we need. And academia goes up and they develop new degrees. And here in 2023, we are developing here at San Antonio College a new Associates of Applied Science in Data Science and Artificial Intelligence. And really, when you think about all the different tools that are within the domain of that degree, it's not like they're already not somewhat covered within the various disciplines across SAC. It's just that we're coming up with specialized focused programming in order to meet that industrial demand in that space. And an example of this, if you look at the creation of the electrical engineering program at MIT, and I have the link that I took this quote from beneath, but in September 1882, you have Edison opening his first commercial power plant in the US in Lower Manhattan. So clearly that creation of kind of electrical distribution is going to create significant demand for employees, right? So that same fall, you look at MIT making history of its own and creating its own electrical engineering curriculum. And if you dig into that article, and sometimes that article goes in and out behind a paywall, so if you have any issues accessing it, shoot me an email and I'll see if I can help you. But you will see there was a lot of debate amongst the faculty at MIT because they said, hey, a lot of these principles that engineers working in the power industry would need to understand, basic electrical theory, thermodynamics, and so on, they're already covered within our mechanical engineering degree. So why do we necessarily need a new electrical engineering degree? So that kind of debate about whether or not there's need for a new specialized track within engineering is something that's been ongoing for hundreds of years now. So if you look at kind of the current ongoing evolution, I put Carnegie Mellon there, having a new Bachelor's of Science dedicated in artificial intelligence, and University of Hartford, with a Bachelor's in robotics engineering. I think the hardware there thing got to me when I was getting ready to say robotics. So when I think about, at least in my opinion, and this is not a rule of thumb, what really kind of defines the two subsets or domains of all the engineering subdisciplines is everything I view as a classic case of electrical or mechanical engineering. And a lot of this is dated by when I did my undergrad in the early 2000s. I viewed, of course, computer engineering is certainly a subset of electrical engineering, and that's reflected in the department design of lots of electrical and computer engineering programs, including at UTSA. You can kind of view computer engineers as just electrical engineers that are particularly focused on computers as electrical subsystems. Civil engineering, it would be hard to argue that that is not really a subdiscipline of mechanical engineering. If you look at the program of study, it kind of is set upon a foundation of classic Newtonian mechanics, particularly statics and dynamics, well, hopefully not too much dynamics in most civil structures, strength of materials, and so on, vibrations, a lot of similarities in the curriculum, really just differentiated by the scale of the application domain that the two engineering subdisciplines are working on. Biomedical engineering is kind of a weird one because you have some biomedical engineers that are more EE focused. You have some that are more ME focused. Maybe the people that are doing new tissue design would need to have more domain expertise in areas like strength of materials and so on, versus if you're doing medical imaging, that's naturally something that falls more under the domain of electrical and computer engineering. But that is a blurred line, particularly as we get into really kind of, I would say, is a lot of the really advancements in technology. in on the biomedical sciences side of things start to actually transition into reality, and those roll over into the engineering domain. Biomedical engineering is kind of going to have these things that don't really fit well under that electrical and mechanical subdiscipline. Segmentation. Chemical engineering and mechanical, at UTSA, it is housed within the biomedical engineering department, but usually you think of it as kind of a specialty or subfield of mechanical engineering, even though that one's a little bit tough. But really what I'm doing there is just focusing on the heavy reliance on, from an engineering point of view, thermodynamics. One could argue that chemical engineering has so much specialty coursework in kinetics of kind of physical chemistry that really it's kind of a better alignment with classical chemistry, and that would certainly be true. But under the engineering domains, probably a better fit within ME. So this is what I was talking about a little bit earlier, that when you pick your subdiscipline, you not only want to be concerned on the fact that you're kind of aligning yourself with the type of problem domain that you want to work on, but you also need to be cognizant, particularly if you have a family that you want to live close by, that you're considering the geographical factors that may influence employability in a particular region. So here on the top, I have the states with the highest employment in mechanical engineering. You certainly wouldn't consider Michigan an economic hotbed. My PhD is from Michigan State. I spent a lot of time in Michigan and grew up in neighboring Ohio. However, you do see that there are the largest, at least when I took this data, number of mechanical engineers working in the country are in Michigan. And then if you look at that from a density point of view, of course, given that these two states underneath, California and Texas, are much larger, Michigan, from a density perspective, has tremendous employment in mechanical engineering. And of course, that's directly associated with the prevalence of the big three automotive manufacturers, at least historically viewed as the big three. I realize that Chrysler is no more and is kind of under the Fiat umbrella, but they still have a tremendous presence in Michigan. And one of the things that you've seen in that area is even as the market share of the big three within the United States has eroded to some respects, foreign manufacturers have moved a lot of R&D operations, particularly into the Ann Arbor area. So like Toyota has a big research and development presence in Ann Arbor, Michigan. So where I'm going with that is you might offhand think, oh, I want economic opportunity, I'm not moving to Michigan. Very few people have said that, right? Particularly since the 1960s, probably. However, because of the industrial concentration in automotive up there, if you're going the mechanical engineering route, that may someday you may get an offer that your best option is to move to Michigan. So if that's something you want to do, that's definitely something to think about. You'll notice that Pennsylvania and Ohio in the top 5 as well for mechanical engineering employment opportunities for those same reasons as Michigan. When you look at electrical engineering, probably not surprised to you, maybe immediately you think of computer engineering in Silicon Valley and California there at the top, with Texas being second. I think one of the things you'll find is electrical engineering, and I can talk to any of you in detail that are interested, is so segmented from an application point of view that if you had to rely on one engineering discipline as giving you employment opportunity across the entire country, it's probably it. But I want to preface that by saying that you have to be careful about what application domain you're working in. So if you're working in power distribution across the entire country, right? If you're working in solar, maybe not Maine versus opportunities that are kind of in that sweet spot of latitude for solar in the Tennessee region. But who knows? Maybe there's a company working on solar design in the Northeast. One of the things that I wanted to say here, in addition to geographic factors when picking your subdiscipline, also be cognizant of the fact that a lot of these rules of thumb have kind of eroded in the post-COVID environment, where working remotely is a greater opportunity than it used to be. You could argue that recently maybe the return to office phenomenon is picking up some steam, but still, even with that in place, certainly more opportunities to work remotely than there were pre-COVID. In addition, one of the things you want to think about is what kind of employer you want to work in. Do you want to work in a startup? Do you want to work in a large corporation, and so on? And we can go into more detail if any of you have questions on that. But also whether or not you want to go to graduate school, particularly for biomedical engineering. A lot of times people want to work in that particular field, and because more of the jobs are associated on the design and fundamental R&D function versus more mature, kind of lower risk levels of engineering functions, oftentimes those jobs require a graduate degree in order to get them. So there are some employability issues as a function of your terminal degree that you need to think about. So when you think about the difference of engineerings versus technicians, this is another thing that people talk about, and oftentimes they'll put scientists as another bubble in here that you try to draw a Venn diagram and distinguish. I think it's just important to think about the kind of differentiation between what makes an engineer and what makes a tech. If I had to talk about the two factors that traditionally cluster those two vocations, I would say it's the level of education, particularly the mathematical basis within the education. I used to teach in an electrical engineering technology program, and they took a principles of calculus class, but it was actually called tech math. And, it's just not as rigorous as a traditional calculus sequence basis of courses. And the reason is oftentimes engineering technology degrees, kind of those individuals want to conclude their education at the 2-year point. So you just got to jam a lot of stuff in 2 years, and you want to give them a background that's appropriate with the type of problems that they'll be working on. Another thing that you might use to distinguish the definition of an engineer from a technician is the type of activity that they're doing. If it's someone that's working in troubleshooting or maintenance or fabrication versus the actual design point of view. And just a really simple way to put that is more often than not, most people would agree that individuals that are working with their hands more than maybe pencil and paper or computer maybe would have a greater likelihood of being a technician versus an engineer. But those are very, very blurry lines. And in fact, what I mean by this second bullet point is if you're an engineer and you have those hands-on technical tools, particularly in emerging technology areas like rapid prototyping, 3D printing, the capability to do electronic assembly and soldering and so on, those are not usually in an engineering science curriculum. We're too busy doing Laplace transforms and these sorts of things and theoretical analysis. So if you can pick them up as part of your kind of extracurricular activities through projects, one of the things you might find is you have additional employment capacity, particularly in small businesses that can't necessarily afford to hire a technician and an engineer. They need their engineer to fulfill a lot of the functions of the technicians. So when you think about kind of the world perspective of what engineers do, here's an interesting study. It's getting a little bit outdated, but it's from 2013. And it was a survey of 3,200, and NSPE, we'll talk about later on in this lecture, is the National Society of Professional Engineers. So a subset of engineers that went through the professional licensure process. They surveyed these engineers and they said, hey, what do you think the public actually thinks about you? And they agreed that public perception was generally positive, but that the public generally had no clue what engineers did. And what a sad thing that is when you look over at this infographic to the right in the 20th century of all the accomplishment of engineers in the 20th century, right? We've impacted everyday life to a point that we've almost become ubiquitous. Like people they take for granted a lot of the things that engineers have brought to society. So that's a really the key point that I would like to emphasize with this slide is that's why it's important to support outreach initiatives, particularly in 2023, 2024, 2025, when AI particularly gets more and more prevalence and everyone thinks they just want to go write code. Everyone can't write code, and AI is going to be prevalent across all of the domains of engineering. So it's important to still have people that are very interested in different application domains within engineering. So if you do outreach, if this survey is true and the public is not aware of what we do, who's going to tell them, right? It has to be us. And that's why outreach is important, particularly amongst historically marginalized individuals who would naturally know what an engineer does. Well, it's going to be people that maybe grew up around engineers, or their dad is an engineer, or their mom is their engineer, or uncle, whatever it may be. So like someone like myself, I told my story in the intro video. I had no clue what an engineer did because I didn't know an engineer when I was in high school. In fact, I always make a joke that at my graduation party, when I told someone I was going into electrical engineering, they said, "That's great. You can come back in 4 years and wire my house." There was just such an intertwining of an electrician and an electrical engineer in their eyes. In addition, one of the values, kind of from a selfish point of view, of outreach is oftentimes those outreach initiatives are ran by local professional societies, which we'll look at a little bit later. So it's a natural opportunity to network and build your resume. I'm going to ask you a question on the homework this week. I want you to do a little bit of a deeper dive into this about the National Academy for Engineering's 14 Engineering Grand Challenges. We talked about in the prior slide what engineers contributed in the 20th century. The reason we need you and the reason we need more and more individuals is who is going to address these kind of critical challenges in our world. And I'm going to have you read through those and kind of see which of those you're most interested in contributing to. I have kind of a vast variety of interests in this space. That's one of the nice things about being in higher education, since your predominant job responsibility for me now, at least, is majority administration, a little bit of teaching. I can take the rest of that time and kind of spread my interest out, versus if I were working in a company, I might be focused on one particular aspect of that. So I hope that you found this lecture video interesting. It's a little bit longer than we typically do. We usually try to make them about the 20-minute mark, but I will see you in the next video.